Okay, guys, welcome back. Today we are starting a new topic which is called as gravitation. This is day one of gravitation. A student just asked me a question like why Albert Einstein didn't consider gravitation as a force. He looked at gravitation in a different manner. He talked about it as in space time. You people don't know anything about space time. Yeah, you might have seen some videos where they simply take a sheet and just stretch it or bend it, and they call it space time and space time warping and all. But it's a difficult thing to talk about. Okay, it's like space time warping and all. It's basically like I'm trying to show a 4D expression or a 5D expression in a 3D world. It's not a possible thing. First of all, okay, your brains cannot interpret what really it is. So that's why I consider Einstein as a god. You can consider him as, because the idea that he came up with is a non-existent idea. It's not something that we feel on a daily basis. That not something that we observe in our daily lives. Okay, yet we still, it's been what, 400 years, more than 400 years, Einstein came up with the idea of gravitation, but still we study the idea of gravitation because as long as we don't travel near black holes or near heavy planets or at the speed of light, the topic of gravitation, that the idea Einstein came up with, is totally holding good. Okay, it's not really affecting anything. So we can follow the topic of gravity as long as we are not talking about black holes, as well as long as we're not talking about speed of light or electromagnetic waves. Okay, but when we talk about quantum physics and all, we can't talk about gravitation anymore. But as long as you are just dealing your daily life on the planet surface, yeah, gravitation is a totally acceptable topic. Aniket, what is it?
Sir, Newton came up with gravity, right, sir? Not Einstein.
No, Newton came up with gravity. Einstein's idea is debunking the idea of gravitation.
Okay, sir.
Did I mix up with the names?
Yes, sir. You said 400 years ago, Einstein.
I'm sorry. 400 years ago, Newton came up with the idea. I'm sorry. But yeah, we are still following it because we are just living on the surface of Earth, right? So as long as we are here, it's totally fine to follow the idea of gravitation. All right. So that is one thing. Now, talking about gravitation, there we'll be talking about basic things like what is the force in between two masses, or what is the force in between two planets, or one planet, one satellite, Earth and Moon. We will be talking about Sun and Earth, their behaviors, how they go around each other and all. We will be talking about all these things. But before I start this topic, I want to clarify a lot of doubts people have. Like one stupid doubt, it sounds extremely stupid. It sounds extremely stupid, but I'll discuss it anyway, because there is a student who asked me, like, when I draw a thing like Earth, and I asked him, where do we live on Earth? Where do we live on Earth? On the surface or inside the Earth? He that student he didn't even have an idea that we actually live on the surface of Earth. He thinks we live somewhere inside. Okay, that is, I don't understand why he thinks that. And he even had a doubt that if a person stands here, how can he stand there? What if he falls off? That is a question that he asked. I know it's extremely stupid, but I just want to clarify that if you are on Earth, gravitational force is acting towards the center of Earth. So no matter where you're standing here, it doesn't matter. The gravitation is still acting towards the center. Nothing is acting in this direction. There is no other forces like that. Okay. Yeah. These were the doubts that's supposed to be cleared in kindergarten, but uh, I came across a student who thinks this. Okay, he was really, like convinced with that idea. But so I had to, you know, tell this every year. I just do it. Yeah, this idea might sound stupid. Coming to the next ideas, how planets go around, how Earth goes around the sun. Is this a circular orbit or elliptical orbit? Anybody? I'll just give you a chance to unmute yourself for a while, okay? Just because we need to ask a lot of questions. So, what kind of an orbit is this?
Elliptical orbit, sir. Elliptical orbit.
Elliptical orbit, sir.
Elliptical.
Yeah, yeah. Everyone says it's an elliptical orbit. So, can I draw the orbit something like this? So, if this is Sun, uh, is this like the orbit?
Not this much, sir. Not this
No,
much
no, sir.
elliptical.
Sun will
It
be
was
at the center of
ball.
lines diagonals, sir.
No, what?
It is like that
Sun
only,
will
sir.
be at the foci, sir.
This is the focus. Like, if I have this animation opened here. So, yeah, look at this thing. So if we run this thing, let us just say that is sun and that is the planet. We will talk about all the areas sweeping by the planet. We will talk about it. But you clearly see that the planet is getting really close to sun and it is getting really far to the sun, right? Can somebody tell me what happens when planets get really this close and planets go really far
Its
away?
velocity will increase, sir.
And what happens here and what happens here? Any other effects?
Sir, V is equal to R
Gravitational
omega
force
thing.
decreases and increases, sir.
Also, we experience this thing that the gravitational force increasing and decreasing.
No, sir.
We don't experience, sir, because we are in the gravity of Earth, not in the gravity of Sun.
Oh, oh, there is a thing called gravity of Earth, and there is a thing called gravity of Sun.
Sir,
No,
no, sir. It's like the gravitational pull is so minuscule, sir. The
the
difference is
Sun, the gravitational
minuscule.
pull is so weak that it
Okay,
doesn't.
okay, we will come back to this thing like gravity and no gravity. Please remind me about this thing. No gravity space or gravity free space. We will talk about this thing. But clear me this: when we get here and when we get here at these two positions, don't you think are we getting like too close and too far? Is this causing? Someone actually said texted saying the seasons occur because of this. How
Yes,
many
sir.
of you agree with this thing? The seasons actually occur because of this.
Sir, I do.
Me,
Sir,
sir.
seasons
When
are
I do.
When it is close, it's summer, sir.
How many of you don't agree? Let's talk about that. How many of you don't agree? Plus, people who don't agree to this statement, seasons occur when the sun
Sir,
is.
it is just in factor, sir. It's also seasons also depend on the tilting of that axis of the
Yes,
Earth.
sir.
No, let me ask, just answer this question. Is this affecting the seasons or not?
Yes, it is affecting.
Like, so when we are here, it is summer. Is that what you people are saying? When
Yes,
we are
sir.
here, it is summer, and when we are here, it is
I
winter.
think no, sir.
Is
No, it
someone's
doesn't
going to
work like
disagree
that.
with this idea?
Me,
Zaid.
yes, because different countries have different seasons, right? So
Exactly. The idea that you people just came up with is the stupidest idea that I've ever came across. Okay. It's not exactly, I mean, it's acceptable that a lot of people still don't know this, but seasons don't occur because of this.
wait, sir, is this actually true that the Earth comes closer?
Let me show it to you. Yeah, it definitely does show an effect, but that is not the reason. Okay. If it is sun,
Sir, only Australia.
Earth actually
Sir, only.
goes in an elliptical orbit, but the elliptical orbit almost looks like a circle. Okay, that is the biggest misconception a lot of people have. That almost looks like a circular orbit. So it's slightly like. Are you done with the topic ellipse in mathematics?
No,
No,
sir.
sir.
No,
Not yet.
There is a thing called eccentricity. That eccentricity decides how squished the orbit is. Like if this is a circular orbit, if you increase e, it gets squished. Okay, the value of e for Earth's orbit is very, 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 very tiny. It's like so little, so it's almost a circular orbit only. Okay, mathematically speaking, it is an elliptical orbit, but it is not really that elliptical. Okay, and to frankly speaking, these distances they don't change a lot, and it might come as a surprise to a lot of people who are watching this video or this class. We are in winter right now, but in Australia this is summer. You know that, right? So
Yes.
what do you guess?
Yes, sir.
So
Because of
it is,
tilting.
according to
Because of
your
the
theory,
axis.
the closest point is
Excuse me, sir.
yeah.
Sir, you showed us one ellipse with a high E. And then asked us, this is cheating, right, sir? You could have shown the
Exactly.
real
That
one.
is you're supposed to say that is not the kind of ellipse that we have. Okay. So this is not the sun. You people think this is summer, so which means this is winter. So now we are in winter, and Australia is here. Like India, the Earth left Australia here and came here. You people are being stupid. No, this is not how it happens. Please try to understand that bit. Let me clear that bit to you people first. Okay. It is because of Earth's tilting. Redmi 9 Pro Prime. Who's that?
Sir, I have a doubt.
Yeah. Who's that?
I
Zahid, tell me.
think, yeah. The thing is, I saw a video on Instagram that like he took a cloth, he held it, then he put a heavy mass, then he put some balls. He said that like when planets revolve at a certain time, they'll go into the sun. I didn't get it.
I can't make out your voice. It's really I mean there's a lot of disturbance.
Okay,
Sir,
there's a
can I
lot
say,
of
So
sir?
he's
difference.
saying the planets will go into the sun.
Sir, he
Planets
said
will
that.
go what?
Into the
Sir,
Yeah,
sun,
they'll
like
merge into
spiral
the sun.
movement.
It doesn't make sense. Is that true?
Why will the planets
sir,
go into the sun?
Yeah,
sir,
I
he
don't
said
get
that
it
he
either.
saw an
That's the thing.
example, sir.
What?
Like there's a
Yeah.
sheet and so there is a sheet and there are few balls in it, sir, and there's this big ball in
Oh,
the
that
center and there
sheet
are few
video.
small
Like
Yeah.
balls.
again, they try to
Yeah, that video.
express.
Yeah.
Yeah. Raghu just sent me the link. Okay, first of all, the thing that is wrong with the video is, like I mentioned already, you cannot express a four-dimensional idea. You cannot express a four-dimensional idea into a 3D world. That is a first mistake. That is the first problem people are facing. Okay, you cannot express a four-dimensional idea into a 3D world. And second thing, that sheet that they put up a sheet. Wait a second.
Excuse me, sir.
Yeah.
But still we can say, right, sir, like circular motion, it is revolving.
I didn't get you again.
So there's a velocity in the planets and there's a centripetal centrifugal force. So
Huh?
it's revolving. That's it, sir.
I don't understand your voices at all today.
Sir, like how we learned in circular motion,
How
there's
we learned in circular motion?
there's a centripetal force, there's a centrifugal force, and it's
We will talk about all those things, man. Please wait. Centripetal forces and centripetal forces, all. We will talk about them. Let me talk about when I'm clearing the doubt. Just let me clear the doubt first. So that sheet video, like they put a sheet and they put a sphere and all the planets around them, they go around. There is friction in this place. When there is friction, obviously the velocities get lower and lower, and they keep on falling into the main object there. That is not the case with the solar system. In the solar system, there is no such thing as friction, right? And the planets are going in the orbit. There is no problem in that. Okay, and then let me talk about this thing. Where are we? You disturbed me. Yeah, the seasons. The seasons occur because Earth is tilted like this. So when it is in the orbit, you observe these countries, the countries in this southern hemisphere, they are exposed to more time of sun in in this place. Now, when you come to this place, only northern hemisphere is exposed to more the planet. Sorry, more the sun time. Okay. So in this case, you are talking about more daytime here. So all the northern hemisphere people will have summer. All the southern hemisphere people will have winter. And here, in this case, all the southern hemisphere people will have summer. All the northern hemisphere people will have winter. Okay. Sorry for the interruption. Srinivas sir asked us to learn about significant figures. Can you explain? Why would I explain significant figures in the middle of the topic? Come on, guys. You're ruining the day one of gravitation for me. Ouch. Oh, where was I again? You completely took me off my topic.
In southern it will be summer.
What?
So climate, sir. We were in
Summer,
climate.
there you are, sir.
Yeah, the summer part is over. Like this is the reason why you get summers and winters. Yeah. So that is one of the biggest misconceptions people have about planets going around elliptical orbits around sun. Okay, there are elliptical orbits only, but they're not really. They're quite close to a circular orbit. It's not really extremely elliptical. Okay, so what you're seeing, the animation, the kind of animation that you're seeing, watching right here, is not exactly completely, accurate, but to make it clear, to make it more understandable, they just make an animation like this. And also looking at the, like, do you people know what's this Kepler? Have you ever heard of Kepler's laws?
No,
We
sir.
have heard, but
No,
we
sir.
We
don't know.
lost, sir.
Heard
What?
a few times.
I didn't get you people.
I
Yes,
have
sir.
heard, but I don't know about it.
Everyone speaking at the same time. Today is a bad day to start a class, I guess. Anyway,
No, sir. I
so Kepler's laws, let me just mute them all. I'll just speak. So Kepler's laws basic idea is the same thing. Like we will come across this Kepler's laws again once we talk about circular orbits, elliptical orbits and all at the end of this topic. Then we'll be knowing about all the things, what are happening here, the angular velocities and the time periods of this thing. We will come across these things. Like you might have heard these three laws. In HC Verma, they are written in the first page itself. They asked us to like discuss it in the first page itself. But I don't really suggest talking about these laws. You don't really know what is happening here. You might understand what's written there. The statements are quite clear. All the planets move in elliptical orbits around the sun at focus. Sun is at focus, and all the other planets are going in elliptical orbits. Like I mentioned, the eccentricity of the ellipse it's not high. It's a very low value. And then the radius vector sweeps equal area and equal time. This is an important task. Okay, like if you look at this animation clearly, in equal intervals it is sweeping equal areas. All the black areas that you're getting are the areas swept by it. And guess what, the time taken for all the points, let me show it. Whoa, it got zoomed away. I didn't do anything. What happened to it? Let me just reload it. Okay, yeah. So what we see right here is the areas. The first area, the second area, and the third area. All the three areas, all the three areas that you're looking at right now, to swipe this amount of area, to swipe this amount of area, and to swipe this amount of area, it takes equal amount of time. Let us say it takes 1.5 years to swipe this area. Should take 1.5 years to swipe the same amount of area, and it should take 1.5 years to swipe the same amount of area. There is an equal easy proof also, but we will come across this thing at the end of the topic, not right now. Okay, we will slowly get to that point to discuss this idea. So that is a rule, Kepler's second law, let's just say. And there is a third law where the square of the time period of the planet is proportional to the cube of a semi-major axis. You don't even know what is a semi-major axis, and people ask us to discuss this. So that is why you can understand point through at the point 3 at the later stages of topic. Okay, now can somebody tell me who is this guy? Of course, yeah, everyone knows who this guy is. Newton. Sai Charan, what is it? What
So
is it?
Newton.
Of course, it is Newton. Except he used to have more hair, I guess. So let's just put it. But I have a question for you people. Look at this. This is a thing that you might have come across already, which is a photo taken from the same position throughout the year. Photo taken from the same position of Earth, of Sun at the same time. Let us just say we look at Sun at 8 a.m. today. So I take a specific position. At that specific position, I will just put it there and the camera. I'll take a photo every morning at 8 o'clock, the same sun. Okay. This is the kind of image that you get. Like one day you get the sun's position at one point, and later on it changes. The position of the sun actually changes at the same time, but different day in a year. Anyone has an idea why this happens? Sai Charan? Anyone has
So
an
maybe
idea?
because the Earth is rotating around the sun, and at the same time we are bending in both directions.
We're bending in both directions.
So that the one which causes winter and summer in two hemispheres, that thing.
So because of the tilting, it is happening. Is that what
Yes,
you
sir.
think?
Tilting and revolving together.
Okay. Let's stick with that. And there are more effects. It's not just this. There are more effects to this thing. Okay. The elliptical orbit that we're talking about, it's not actually the same. Even the elliptical orbit keeps changing of the elliptical orbit of Earth. It actually keeps changing along sun's around sun, but it changes for a very long time. So we don't really need to talk about that. So the things that we learn in school are like very minimal ideas of what we actually experience. Okay, so we don't really talk about all those things right now in this topic. I just wanted to introduce you to all these ideas today. But right now, the things that we are going to learn in this topic, basic laws, the gravitational laws. We all know the stories how the gravitation came, how he came up with an idea, like when he's sitting under a tree, an object falling towards Earth. So then he came up with the idea, it's not just the Earth, sorry, the object falling over it, the in reality both the bodies are attracting each other. The apple is attracting Earth and Earth is attracting the apple. They came together and they meet. So this is true. This is true. Like every time you drop an object from Earth's surface, like from a height, it's not just the object that is moving. Earth is also moving, but the amount of movement that you see in Earth is so little, so tiny that we don't really feel this movement. Okay, so he came up with this theory, and we all know the expression Gmm by r square, the amount of force in between two bodies and all. But we need to learn this topic in much broader perspective. I'm going to ask some questions. I need a volunteer. Somebody raise some hands, and I just want to ask some questions about Gmm by r square only. Just this. Okay, I'm going to unmute all the people who raised the hands. And yeah, guys, my question goes, did I miss anyone? I can't find anyone.
So Vamshi, Sumant and Mayur, you missed them.
What?
You missed Vamshi and Mayur.
Okay, Vamshi and Mayur. Now, the question goes like this. Everyone knows this thing. My first question is, what is G?
Gravity, sir.
Was it-
Gravitational constant.
Gravitational constant, sir.
Who said G is gravity?
I said by mistake, sir.
So the gravitational constant. To be precise, it is called as universal gravitational
Constant.
constant. Now, my first question is, does this change?
No,
No,
sir.
sir.
It's a constant, sir.
Constant.
So it is there for
it
all.
an absolutely constant value?
Yes, sir.
It is constant.
Yes, sir.
No.
Yes,
Is it absolutely a constant value according to Newton, or you can actually use this anywhere?
So it's
You can use it
constant.
anywhere,
It's
sir.
constant.
It's a constant value.
No, that is a thing. That is a thing that we need to talk. Okay, I'm not sure about that, but according to Newton, this value is constant. But I wouldn't really say it is a universal thing. Okay, after people came up with other ideas like relativity, and then quantum physics came in and it changed everything. We can't really completely rely on this constant, but according to Newton's theories, yes, G is a absolute constant. We are totally happy with this. My second question is, what is R?
The distance between
Distance between the two objects, sir.
Distance between two objects.
Center of
Let
mass
us
of
say
two
I have one
objects.
object,
Center
I have
of
another object.
Distance between center of masses,
between
Center
sir.
of mass of
mass
two
of different
objects.
objects.
Yes, sir. Center of mass.
That is a precise way to put it. The distance between the center of masses of two objects. So if this center of mass is here and this center of mass is here, you people are saying that this is R.
Yes, sir.
Yes, sir.
Now,
Yes,
the
sir.
next question,
Yes.
probably everyone will make this, I mean, like give a wrong answer. What is M and M?
The
The
masses.
masses of
The
those two
masses
objects.
of
The masses of two objects. So if I give a situation like this and ask you to write the force in between them, can we use this as Gmm by R square?
Yes, sir.
Yes,
Yes,
sir.
sir.
Can we use this? Everyone agrees?
Well, actually,
Yes,
these
sir.
Yeah.
M's are the point where the masses are fully concentrated, I think.
Which is nothing but the center of mass, right?
Yeah, at that point, the masses, sir.
You are just mixing up
But
all
the
the
force will be same throughout the line, right, sir?
Yeah.
No. The thing is, no, you cannot use this.
So for only point masses can we use, sir?
Exactly. The law of Newton's law of gravitation is actually truly applicable G m1 m2 by r square. This is where our definition starts, guys. I'm just talking about the magnitude for now. G m1 m2 by r square is truly applicable for point masses only. G is a constant according to Newton. Yes, G is a universal constant for sure. And the masses m1 and m2 are point masses, and r is the distance between the point masses. Since it is a point mass, you don't
Excuse
even
me,
need to
sir.
talk about the center of mass again. Who's this?
So we can consider extended bodies as different points and then say it is applicable.
Let me talk about it. So yeah, this force of gravitation that we just talked about can be written for point masses, but when you have a random body of mass capital M1 and capital M2, and even though we know the center of masses, no, you cannot use this. What you have to do is you have to take each and every point mass in this body. You have to take each and every point mass in this body. You have to write all the forces present in between them, all the forces. It's a resultant of all the forces that gives us the answer. It's a resultant of all the
You'll
forces
have to integrate it, right?
that
sir?
gives us the answer. Okay.
How to do that, sir?
What?
Sir, so many calculations.
Yeah, but turns out when I have a spherical body, I can happily use the same idea in a spherical body, uniform spherical bodies. Okay, both are uniform spherical bodies, both center of masses are at the centers, and the distance in between them is r. Yes, in this case you can gladly use gm and 2 by r square, and the forces are totally, this idea is applicable. Now what is so special about spherical surfaces?
Sir, the
It's
corresponding
uniform.
points are always have a same distance from
Same
each other.
distance
Sir.
between them,
Yes,
sir.
sir.
They're
What?
equidistant from the
Sir, every corresponding
common
points
point.
has same distance.
Same distance between them, sir.
No, it's not true. We can just simply say this is a coincidental thing. It's
It
just a
resembles
coincidence
a
that
point.
it is only defined for point masses and it is also working for spherical bodies. Or you can actually mathematically prove, by taking a small ring, and in the ring you take a point mass. It involves a lot of calculation, for example, for sure. But the forces are, in the end, mathematically you will prove the force comes as simple as gm and m2 by r square.
Excuse me, sir.
Yeah.
So we can even intuitively say this, right, sir, that every corresponding point on both the spheres will be the same distance.
No, it's not. Okay, that's what you're thinking, right? Like, let us take
Yes, sir.
two spherical bodies, but if you take this point, I have to take all the points in this mass. If you take another mass, you have to take from all the points in this thing. If you take another point, you have to take all the masses in this thing also. So no, the thing that you're thinking right now is not the proper idea, in my opinion. You get that?
Yes, sir.
Yeah. So one more important idea. Yeah, so like I said, it is just a coincidental thing you can say, or you can actually mathematically approach and prove that it is actually working. Okay, so let's just settle with that. But there are more things to talk about. Okay, like what are the more properties of what are the proper ideas, like how do you actually define this force properly? Whenever you have a point mass, I will be talking about point masses only. Okay, I won't be bringing any spherical masses anytime soon. Whenever we start talking about planets and all, then we'll definitely bring all the other objects, but for now I'm only going to talk about just the point masses. So m1, m2. First important thing is, now can you people tell me whether this is called as a action and reaction thing?
Yes, sir.
No, sir.
How many are agreeing with it? Can we
No,
call
sir.
it as
No, sir.
action and
I'm
reaction?
No,
agreeing.
sir. We
I
can't.
agree, sir.
Sir, I disagree.
Yes, we can actually agree, because action and reaction pair, remember this part, action and reaction pair, they always act on different bodies
Different
like
bodies.
m1 and m2, and they are always equal, they're always opposite to each other. So these two, this the pair, the force, the gravitational force that is acting on these two bodies can be called as an action and reaction pair. So in that is the thing that we talked about in Newton laws. When I say a body is resting on the ground, we've talked about all the forces. We've talked about mg, we talked about normal force on this, normal force on the ground. So these two normal forces are action and reaction pair. Then where is the reaction pair for mg? Anybody?
Normal force,
It is
sir. No,
provided from
mg
the
from other
center
side,
of
sir.
gravity.
mg on the center of the planet. That is the reaction pair for mg. You get that? So guys,
Have one
that
doubt
is the
here.
that is one more important point. These two forces are clearly action and reaction. They always lie on the line joining them. Yeah, there is a reason why I should mention this point, because we will come across some forces in future like magnetic forces. They won't lie across the line, they don't actually go along the line, they actually go perpendicular to the line. We will talk about this thing later, but the importance is these two forces are clearly central forces, like they are acting towards the centers, onto the centers, and they clearly act on the line. This is a very important point. Can somebody tell me whether the gravitational force is a conservative force or not?
It is conservative, sir.
How can you say that?
It is conservative.
So that is what we learned in the chapter.
No, you can actually prove that by doing something. We will do that. Okay, like in 1 hour, not 1 or 2 days, maybe next week we will actually try to prove whether gravitation force is a conservative force or not. But these are the basics. Okay, like these are the basic ideas that we need to talk about gravitational forces. Like these they are action and reaction pair, they are conservative forces, they are central forces, they are acting towards each other, onto the centers only, on the center, towards the center. Okay, and
Excuse me, sir.
yeah.
Sir, when we are applying this gravity, this mg thing for applying on Earth, is it correct to consider from center of mass only?
Yeah, it is correct to consider on the center of mass.
We'll not do like for every point how you showed, sir.
It's not really true to consider center of mass. It's actually true to consider center of gravity.
Sir, I have one doubt, sir.
Yeah.
Sir, then why Earth and Earth's orbit around the sun in a circular path, sir? Then if they are having forces like which will make them collide, then why are they not colliding?
We will talk about the orbits. Okay, you will get a complete clarity of orbits, of elliptical orbits. We all think only circular orbits are stable, but even elliptical orbits are also stable. We will talk about that. Okay, we will come to those conclusions later. Elliptical orbits are also completely happily stable. Okay. Yeah.
So what is center of gravity?
Center of gravity,
Yes, sir.
in this topic we will talk. Okay, and it is like center of mass. Just like that, you write m1 r1 m2 r2 m3 r3 by m1 plus m2. We actually write weight m1g r1 plus m2g r2 plus m3g r3 by m1 plus m2. Yeah, you might think that it is just a g which is common in everything, right? But there are situations where g can change. The value, the small value, the small g can change. So we will talk about it, center of gravity, later. Okay, so the question that you asked, center of gravity is more precise speaking about it. Okay, let me.
Sir,
Okay,
one more
more
thing I
doubts.
want to add, sir.
What?
Uh, you told us, sir, G is not constant. On Earth also, it is not constant, na, sir. At different point, we
We
have
will
different G's,
talk
but
about
G is
it.
taken
We
as
will
constant.
talk about
Excuse me,
it.
sir, one small doubt, sir.
Okay. Tell me.
Sir, is it more correct to take along the center of mass or take every point on the body?
We will talk about it.
Okay, sir.
Okay. Let me finish this, please, guys. So we've just learned about some of the properties of the basic ideas of to gravitational forces. So we are always going to use this on point objects or spherical objects. Now you people don't talk. We either use this on point objects or spherical objects. If the objects are not point or spherical, they take different shapes. We will find ways to find the forces. Okay, don't worry about it. Now, one more important idea, like how do we write it vectorially? There is a way. There should be a way to write it vectorially. We'll to put it in a mathematical equation. Let us say I have one mass here m1. I have another mass m2. I want to write this force vectorially, that specific force vectorially. So I'm going to write this thing as r12 vector. This vector is r12. So clearly watch this, guys. I'm going to write the magnitude first of all, g m1 m2 by r12 whole square. But I also want the vectorial representation. I want f2 because of 1. I want force on 2 because of 1. I want this vector. Now clearly watch, the vector direction is along r12 only, but in the opposite direction. Can I write minus r12 cap? Did it make sense to you people? I've mentioned the magnitude clearly. The magnitude is clearly mentioned. Now that this part, the left right side part, is clearly giving us the direction. If only somebody is asking to find f on 1 because of 2. So now I'm writing f on 1 because of 2. The magnitude is exactly the same, g m1 m2 by r12. It's just a magnitude r12 square. Now I simply write
So
r.
why do you need to put mod?
I'm just mentioning that is a magnitude, that's all. Okay, so that the equations look complex, right? So that is why I'm just mentioning it. Do you understand this bit where I put the cap vector, like the unit vector?
Yes, sir.
Yeah. So people actually do things like they multiply with the magnitude again and they make this as cube and they write this as a vector directly, and this as cube and this as vector. This also makes sense entirely. There is no change at all. So just like keep your eye on this thing idea, because you might come across this idea. That's why you are totally fine with the simple formula like gm1 m1 m2 by r square, as long as you are doing simple problems. But if only you come across a complex equation where there is vectors involved and everything is involved, that is where you use this idea. So just keep an eye on it. Okay.
So why do we need that cube and all? We can just put positive or negative, right, sir?
Like instead of writing the unit vector, you actually write original vector. People just do that just for fun. Like there could be some uses because of that. Okay. Instead of
Okay,
writing
sir.
g m1 m2 by r square, just leaving it like that, I also mentioned the unit vector direction. Now instead of mentioning the direction, I only write the original vector, because I multiplied with r, I multiplied with r again, so it's r cube now, just for fun. Okay. So just remember these ideas if you come across these things. We will do some problems on this thing. Okay. Like maybe right after your exam on Sunday, we will come across some of the problems, but I won't discuss them any of the problems today. It's like simple problems. They give mass m, mass 2m. What is the force acting in between them? And mass m, 2m, there is another 3m here. What is the force acting on m because of these two? Like let us say there is one force and there is another force. There are two forces because there are two masses. So what is the net force? And there are other problems, like they put masses like this, m and m and m. There is always forces in different directions. So how much is the force? What are the forces? The first 10 problems in HCFM are actually based on these ideas. we can, if you really are that enthusiastic about these problems, you can actually start these problems on HC Verma, the first few problems. Let me take you across that. But I don't want to do that today. This is just an introduction class, right? So you can kind of take it easy for today. You can prepare the old topics for this week's syllabus. So yeah, all these questions in exercise 1 are basically based on that only. So you can solve these basic questions if you want, but I will discuss these questions tomorrow anyway, so you don't have to really worry about it. All right. Anything else, guys? Anything else from today's class? Please don't bring any new doubts. If you have new doubts, please text me. We will discuss that tomorrow. Nothing else? That's cool then. Let's come back to this topic again tomorrow. We will have to learn a lot. We'll slowly take these things forward. Okay. So thanks so much, and we will meet again tomorrow. So bye bye.
Thank you, sir.